So today we're going to switch our thinking over to geometric sequences. This is going to be Unit 1-D, Geometric Sequences. It's in Chapter 8 in the book, Section 6. You're going to notice we're kind of jumping around a little bit in the book. It's just the way it goes with our current curriculum. So just go with it. It's all good. So we've just finished talking about arithmetic sequences. And remember that with an arithmetic sequence, it has something called a common difference. Do you remember what that was? You could tell that something was an arithmetic sequence if it was either adding or subtracting the same amount from one term to the next term all the way through the sequence. Well, you might want to guess, what do you think geometric sequences are? You might already have an idea. Think about that. So today, let's talk a little bit about that. And our objective is going to be to write N-1 explicit rules for geometric sequences. Now, you're going to notice that there's nothing happening here about a simplified rule. So just realize we will talk about where we use geometric sequences in our next video, and you'll see where we'll kind of deal with that explicit rule. That is a simplified rule, rather than N-1. So we're going to start today, just like we did with Gumby and Pokey. This time we're going to start with something called Sierpinski's triangle. And basically we're going to take this triangle, and the numerator here is the number of red triangles. There's 1. And the bottom is the number of total triangles. So it's 1 out of 1. When we move to the stage 2, the second picture, you're going to notice 1, 2, 3. There are actually 4 triangles, and this time 3 of them are red. Do you understand where this ratio is coming from? Okay, so what I'd like you to do right now is in the stage 3, can you write what the top and bottom numbers would be there? Well, the first thing you got to count, and you've got to be careful here, because notice that the triangles got smaller. So this is not 1. If we're talking about all the same size, there are actually going to be 4 white in here, if you understand what I'm saying. So there's 1, 2, 3, 4 times 4. There are 16 total little triangles. Now, how many of them are red? That's pretty easy to count up. And did you get 9 out of 16? Do you understand that now? So look at this and think of it as a sequence, okay? And look how it's changing. And can you come up with the next term, which would have been the stage 4, without looking at the picture? Can you come up with what that would be? Can you see the pattern here? So notice that I'm multiplying the bottom by 4 times 4, and I'm multiplying the top by 3 by 3. So if you continue that pattern, 9 times 3 is 27, and 16 times 4 is 64. And I'm going to show you this picture. It's kind of crazy. But again, remembering that inside this triangle are a bunch of white, and inside each one of these. So there are actually 64 triangles that are this size that I'm tracing in there. 27 of them are red. So if we take this as a sequence, 1 over 1, 3 over 4, 9 over 16, 27 over 34, it is not arithmetic. We're not adding the same amount each time. But as we just talked about, we are multiplying. So the bottom is getting multiplied by a 4, and the top, the numerator, is getting multiplied by 3. We're multiplying by 3/4. This is not an arithmetic sequence because we're not adding or subtracting. This is going to be what we know as a geometric sequence. So a geometric sequence is a sequence in which the ratio between any 2 consecutive terms is the same. Now, when that ratio between 2 terms of a sequence is the same, that ratio is called the common ratio instead of common difference. So in a geometric sequence, we have something called a common ratio, and basically it is the number that you are multiplying by from one term to the next. If you notice that it's division, like the sequence is going down, like the arithmetic was subtracting, you're still going to talk about it from the multiplication side of things, but instead of saying divided by 2, you would say multiplying by 1/2. Those are the same operations. So we will see that as we go forward. So here is a geometric sequence. So, 3 to 12, 12 to 8. So you can see it's not arithmetic, because if it were, we would be adding 9 repeatedly. So the next thing is there a number we're multiplying by repeatedly? And you'll notice times 4, times 4, times 4. So we are multiplying by 4. That would be called the recursive rule from our very first video a long time ago. And since this is geometric, that 4 is called the common ratio. Now notice this time the sequence is going down. Okay, so, we're not subtracting 80. That doesn't work, so it's not arithmetic. But to go from 100 to 20 and 20 to 4, you can kind of see it right here in 4 to 5. It looks like you are dividing by 5. That is the pattern. You could say that is the recursive rule. But when we're working with geometric sequences, we're not going to talk about dividing. We're going to talk about multiplying. Dividing by 5 is the same thing as multiplying by the reciprocal, which would be 1/5. So the common ratio would be 1/5. So with geometric sequences, we're always going to kind of come off the multiplication side. So find the next terms in a sequence, and we're also going to find the common ratio. So if you can go ahead and take a look at these, you're going to pause the video, stop, write on your notes page the common ratio for 3, 4, and 5 in the next two terms, and turn the video back on, and I'll be ready to check with you. Okay, so the common ratio here, times 3 times 3 times 3. 27 times 3 would give you 81, and 81 times 3 would give you 243. Now here, I noticed some different things going on. And the first thing is it goes positive, negative, positive, negative. That's interesting. And then it is going down. So it looks like I'm dividing by 2, dividing by 2, dividing by 2. Now we're going to have to put a multiplication over here. So it would be multiplying by the reciprocal, there we go, times 1/2. But in order to get the negative, we're going to have a common ratio with a negative. And oh, by the way, it is absolutely okay in this case that if you put times negative 1/2 or times negative 0.5. Now, what does the negative do? If you take a positive 120 times a negative 0.5, you'll get a negative. If you take that negative 60 times a negative 0.5, you'll get a positive, and you'll see that it will alternate signs. So the negative 15, basically we're cutting it in half, but a negative times a negative would be a positive, and our next one would be 7.5. And again, if you wrote 7.5, that's fine. And if you wrote 15/2, that's fine at this point, because there's no decimals or fractions in this original. So you can use either. And then if we take the 7.5 times the negative 0.5, this time we'll get a negative 3.75. Now this one has decimals, so we're not going to be using fractions. So we're going to keep giving it what it needs here. So what is the common ratio? Do you see you're doubling? So you're multiplying by 2. And again, it's positive because we're not seeing that alternating sign. Then we're going to take 8.6 times 2, which will give you 17.6. And 17.6 times 2 is 35.2. All of these are geometric sequences, and this is called the common ratio. Always multiplication. Now we want to write that explicit n-1 rule. That's where we're heading next. And this is going to look familiar to what we did with the arithmetic. So I'm going to give you a geometric sequence. It's right in here. First term, second term, third term, fourth term. 3, how do you get to 15? 15, how do you get to 75? What's the common ratio? Do you see that you're multiplying by 5? That is a dot, not a negative. So it's times 5. I just didn't use the X there. So all of these are multiplication signs, okay? So now let's go back to that idea that we did with arithmetic and see A of 1, the first term is 3. So in the first spot is a 3. In the second spot, you take the 3 times 5. Are you with me? There's the 15. Now the 15 drops down, and we need to take that 15 times another factor of 5 to get the third term. And that would give us the 75. And then that 3 times 5 times 5, which would be 75, we're going to multiply by 5 again. and that would give us the fourth term. So this time what you're going to notice is there's our first term. Just like the arithmetic sequence, that first term is going to drop in. This time we're multiplying the common ratio. That makes sense in a geometric sequence, and the common ratio is 5. But notice that when we're multiplying, we're not like, it has to involve an exponent. It's no factors of 5 here, just a 3. 3 times, oh, by the way, 5 to the 0 is 1. If you don't remember that from your exponent rules back in 7th grade, check it out in the calculator. 5 to the 0 is 1. So 3 times 1 would be 3. Now I want 3 times 1 factor of 5. 3 times 5 is 15. Now I want 3 times 2 factors of 5, 5 to the second, which would be 3 times 25, which would be 75, and so forth. So now when we're talking about the nth, we would need the 3 times 5 to the raised to the, but be careful. Notice that when we have a 4 here, we have a 3 there. It's 1 less factor of 5. And that's where the n minus 1 is going to come. So to write an n minus 1 rule for a geometric sequence, you would take the first term's value times the common ratio raised to the n minus 1. Well, let's test this. Let's put in 3. So we would take 3 minus 1, do our parentheses first. 3 minus 1 would be 2. Then we would have to do the exponent next. 5 to the second would be 25, and 3 times 25 would give me 75. So here is our geometric sequence n minus 1 rule. And I'm just taking a second here so I wouldn't forget to mention this. When you're doing exponents on the calculator, again, remember these are what the keys will look like. On a TI 30 that normally we would have in the classroom, you've got what is called the caret. That'll also appear on like a TI-84 graphing calculator. X to the Y or Y to the X might be the key on your calculator. It is on my phone. If I use the calculator on my phone, you remember you have to turn the phone sideways in order to see the scientific calculator. That's what mine is. But that is the button when you try to raise 5 to the, you need to hit one of these buttons. Okay, so here is our general rule, just like we did with arithmetic. This is our formula for geometric sequences that you might want to put on your notes page. Now remember that this a to the n is going to be the value of the nth term. So if n is 100, it would be what number is sitting in the 100th position of the sequence. Remember that a is going to be the first term of the sequence, which in this case was 3, times, because it's geometric, the r is the common ratio, the number that we are multiplying from one term to the next that stays the same all the way through the sequence. And make sure that you understand that this n minus 1 is not multiplied. It is raised to the n minus 1. It's an exponent. And that n, again, is the term number. Is it the first term, the second term? Which term is it? So again, I'm going to give you this rule that we just found from the previous page. And we are going to find the 10th. So what I would like you to do right now is to seriously, please, please, please pause the video, take your calculator, and put the 10 in for n and do the math. And the reason I'm being so persistent about it is people can make mistakes in the calculator with the exponent. So I want to make sure that you are doing your calculator correct. So can you please pause the video and find the 10th term of this geometric sequence? Okay, so let's see. When you do this kind of work, it's always what we want to see first is you doing the substitution. Don't go right to the calculator. Show me what you're substituting in. Now with our order of operations, we're going to do the parentheses, and that 10 minus 1 would be 5 to the 9th. So 3 times, and if you do 5 to the 9th, it's 1,953,125. And 3 times that, 5 to the 9th, you should have gotten 5,859,375. Holy cow, that's a big number. Now, I just want to throw out an idea here that we will talk about in the future, but remember that this is an exponent. So this right here is actually called an exponential function. And when you have an exponential function, it grows rapidly. Now I'm going to take a second because everybody watching this video is well aware of a pandemic, the pandemic of 2020, and we've heard about COVID-19. We heard about flattening the curve. We heard about keeping this from growing exponentially. A virus will grow exponentially, and we want to try to keep it small. We want the base number of the exponent to not be really large, because the bigger that base number is and the bigger the exponent is, look how fast it grows. So when you heard this whole term about flattening the curve and exponential growth, this is kind of what we're looking at. And if we can lower that base number, and that's usually the number of contacts that somebody would have that might have the virus, if we socially distance, if we don't come in contact and we have this number here be smaller, then this huge number would be far smaller. So we'll be talking more about that, but I just wanted you to see, wow, what a difference a geometric sequence is compared to the arithmetic. So our last page today, we're already there, guys, is for you to now write the general form for each of these sequences and then find the sixth term. You'll notice I'm using a smaller number because they grow rapidly and get big rapidly. So you're going to pause the video. You're going to write your n-1 geometric function rule, and then you're going to use that to find the sixth term. When you're set, turn the video back on and we'll see how you did. Okay, so if I look here, 4 to 40 to 400 to 4,000, the common ratio would be multiplying by 10. When I go to write my rule, the first thing I'm looking for is the first term. Because it's geometric, it's going to be multiplying, not adding. That common ratio, the number I'm multiplying, is 10. And the other mistake that people make is they forget to make this n-1 be an exponent, not a multiplication. There is no distributive property here, guys. We can't do that. That's why we're not simplifying. It's not multiplication, so it's going to stay like this. And we're going to put a 6 in for the n. 4 times 10 to the 5th. And when I put 4 times 10 to the 5th in my calculator, you should see 400,000. If this is somehow going wrong, like you're doing this right but getting the wrong number, you need to talk to me to check to see what you're doing wrong in the calculator, so that when we meet up, that would be a great question to put on your notes page saying something's going wrong in the calculator. So make sure I remember to ask Mrs. Woodruff. Okay, the next one, ooh, it's going down. And what I'm seeing is 40 to 20 to 10. I'm cutting the number in half. I'm dividing by 2, but remember we have to have that common ratio be multiplying. So dividing by 2 is the same thing as multiplying by the reciprocal, which would be multiplying by 1/2. So I'm going to write my first term times 1/2. And again, there's nothing used here, so you can use the decimal for 1/2, which would be easier in the calculator. Raised caret, right, to the n-1. Again, I'm going to have 80 times 0.5 raised to the 5th. And notice I keep it in parentheses here until it becomes a single number. I didn't need to have the 5 there. And now 80 times 0.5 caret, your exponential button, to the 5th, hit equals, and you should be seeing 2.5. And notice this one's getting smaller. It's going down. Okay, this is not exponential growth. This has a different name. Going down, it's a decay. It's decaying. Something's going away. Decay means to erode, to go away. All right. Now notice the first thing I notice. Ooh, look, it's going positive, negative, positive, negative. That's interesting. And the other thing I notice is if I didn't have the negatives in there, I notice that it's actually getting bigger, right? It's going up from, take the negative out for a second, 0.75 to 1.5 to 3 to the 6. So it actually, we're going to start with our 0.75 times, it is doubling, like 3 to 6, but I have to have that negative in there because the alternating, raised to the n minus 1. You don't often see in the real world a case with a negative on the base there, but theoretically in algebra that could happen. Please note that I have parentheses around that -2, and that's going to be important in your calculator. Did everybody hear that? So when you're raising a negative to an exponent, those parentheses need to be in the calculator. We will be talking about more about that. So if you made a mistake, that might be it. So when I go to put it in the calculator, there's the 0.75 times -2 raised to the 5th. Those parentheses you would use. So 0.75 times parenthesis, -2, not minus, -2, and parenthesis raised to the 5th. You do not really need the parentheses around the 5. It doesn't hurt to have them, but you don't need them, but you must have them around the negative. Did everybody hear that? When you are raising a negative to an exponent, it's kind of important to put those parentheses in. I'm going to be honest, it's really important with an even, not so much with an odd, but just if you get in the habit of always putting the parentheses when you raise a negative to an exponent, you kind of can't go wrong. Should have ended up with -24. Again, if any of these problems went south, like I understand how to set it up, but I'm not getting these final numbers, please put a question on your notes page in the questions section. Check with Mrs. Woodruff about calculator on geometric sequences. So today we learned about geometric sequences. They are a sequence that from one term to the next, you are multiplying by the same number. Oh, by the way, yes, dividing. And we learned something called a common ratio, which is the number that you are multiplying by from one term to the other. If the exponential sequence is going down, then you're going to be multiplying by that fraction. And if it's going up, it would be by a whole number or an integer in this case. Finally, the last thing we just need to be careful is to know the rule. You're going to take a variable times the first, equals the first term times the common ratio raised to the n minus 1. The reason I just tripped up over that is because I forgot to mention one thing, and I'm glad I caught it. I don't know why they use a to the n, or a of n rather, than g of n. Our book does it, so I'm staying kind of with that convention, but it would have been kind of cool, descriptive in my mind, if we had, like a g of n. So that's why when I started to say this, I said, I forgot to tell him. So the only reason I'm using a of n is because our book does, but you can use, g of n, you could use any variable. Again, the function notation is descriptive. What you cannot do is put a of n and then have an x over here. So whatever variable is in the parentheses needs to be the same variable that is your input variable. So let me just say that again since I tripped over. It's going to be your output variable equals the first term in the sequence, the first value, times the common ratio raised to the n minus 1, and that's how you get a geometric sequence. Guys, I hope you all have a great day.